Okay, we are at 13.8 frequency, amplitude, and wavelength. And really, I think I'm just going to finish out the rest of the chapter. There's a few sections left, but they're all pretty short. If I feel it's going too long, I'll go ahead and stop. But we're going to look at frequency, amplitude, and wavelength. And here they've attached this vibrating reed to a string, and it's going back and forth. And you can see here at A, the reed is right at the quiescent point, but it's heading downward, and it's pulling the string with it. Now, notice that there's no arrow here on the reed. That's because that's where it stops, and it's about to come back up. And as it goes back up through the quiescent point, you can see that the red arrow shows its velocity upward. And then as it's at the top, then it's stopped again because it's going to reverse direction. Now notice how this red arrow propagates. Like there's a red arrow here, and this red arrow is over here now because it's transferring that energy to the string. And we can see different aspects. You can see from the quiescent point to the highest point on the string, that is the amplitude. And for a nice symmetrical sinusoid, the downward amplitude is the same as the upward amplitude. And we can see from peak to peak, that's lambda, that is the wavelength. You have to be careful measuring the wavelength at zero crossings, or where it crosses the quiescent point. From here to here, that's only a half wavelength. You have to look at the wavelengths crossings in the same direction. So a downward crossing here, a downward crossing here, that is one wavelength. An upward crossing here and an upward crossing here, that is one wavelength. It may be easier to do it from peak to peak or from trough to trough. So here's at t equals 0. This is the start of it. Here's at t at 1/4 t. It's just moved down a bit, and then at 1/2 t and 3/4 t. That's they're showing you at different points. Now let's continue. Now the velocity is equal to delta x over delta t. Well, in this case, delta x is equal to lambda, the length, and delta t is equal to t, the period. So v is equal to the lambda over the period, and we know that the period 1 over t is equal to 1 over the period is equal to the frequency. So the velocity is equal to the frequency times the wavelength. Now these will be important later on to remember, not only as we're talking about audio waves, but as we get into electromagnetic waves, where the velocity in that case is going to be 3 times 10 to the 8 meters per second, the velocity of light. And the frequencies will be much higher, and the wavelengths will get much shorter. These two formulas are important. Velocity is equal to wavelength divided by period, and velocity is also equal to frequency times wavelength. Okay, I'm going to continue on. Speed of waves on a string. The velocity is, we just discussed, velocity is equal to lambda divided by the period, and the velocity is equal to the square root of the force divided by the density, the mass density. So you can see as if we take a guitar string, if you increase the tightness of it, what happens to the tone? It goes up. The velocity, it goes up. You can make the tone go higher by raising the tension. Now, what happens? If you notice a guitar, the high frequency, the higher tone strings are thin, and the lower tone strings are um, are very thick. They even sometimes have a cord around the cord, so there's more mass density. So if you increase the mass density, the velocity goes down, or in this case, if the velocity goes down, the tone goes down. So there is you know, the working of a guitar string or a piano string. The force is the tension in the wire, and the mu is the mass density of the the linear mass density of the string. Okay, let's go to interference of waves, and you can see here there's different waves, maybe coming from rain drops or some, and you can see that they cross over one another and they interfere with one another. So here's two. If you look at A and B, they are both at the same frequency, at the same phase angle, so that they add. Combining the two waves in parts A and B results in a wave with twice the amplitude. So they just add. It's a superposition of the waves, and they become a larger wave. Now, notice that these two waves are out of phase. A is an upgoing at the start, B is downgoing at the start. If you combine these two waves, the result is complete cancellation. And I'm gonna attach a video where I actually, if you take two speakers playing the same tone, they have a wave coming out of them. Well, if you move the speaker, you can move the speaker to such a point where they're out of phase and the sound disappears. And you can see it both electronically on an oscilloscope, and you can also hear that the tone goes down. And I'll play that. I'll attach a video that demonstrates that, the interference of waves. Okay, here you have these two waves. In A, you have one going to the right and one going to the left. When the pulses overlap, as in parts B, C, and D, the net displacement of the string equals the sum of the displacements produced by each pulse. But once you get to E, the left going one continues with the same shape as the right, and the right going one continues with its same shape. Okay, when pulses overlap, as in part C, their displacements subtract from each other. So you can one is going up and one is going down. They add, and so it's a reduced wave in C. But then they continue on with their own shapes once they get past each other. Okay, reflection of waves. If you have an incident pulse coming at an anchored position, notice the position is anchored. As it hits the anchored position, it reverses direction. The reflected pulse changes a phase. It's a downward going pulse now. Now, if you were to have it loose, if you were to have it on a loose ring, the incident pulse hits is just about to hit the pole. When it hits the pole, the ring goes up, and then the reflected pulse is in the same phase, or it's the same upgoing as it was when it started. I've never been able to reproduce that, but it would be interesting to try. And that's the end of this chapter, chapter 13. The next chapter will be on sound.